Happy Friday, everyone. We're getting down to the wire here. I want to talk a little bit more about confidence intervals today. And I thought it would be a little bit more helpful to go into more depth than what I had in the previous presentation as it pertains to the confidence interval part. I won't spend as much time on the t-distribution this time around, but I will definitely spend more time than I was planning on the confidence interval part. I don't want to give that short shrift. So I've put together a presentation that reflects that. Hopefully you'll find it more helpful, but that's basically what I'm going to be going through now. Okay, so let's get to it. And let's see here. Here we go. So let's go back to the beginning here. So we're doing confidence interval estimation here, okay? And specifically, I just want to talk about confidence intervals for means themselves. And by means, I mean the mean of a population. The goal here, once again, is to use sample statistics to get at population parameters. Okay, if there's one thing I want you to take away from this statistics part of the course, is that, namely, what statistics is doing is getting at parameters for a population by way of samples. And we're trying to do that in a careful way and say precisely what it is we have done. And that involves probabilistic techniques, okay? So a confidence interval is a range of values that are plausible for the parameter of interest. Okay, so again, we could be talking about the mean or the standard deviation. There might be other parameters we're interested in. The confidence level is the degree of reliability of the interval. For example, like if I say a 95% confidence interval, what I'm saying is that whatever parameter I'm talking about, I'm 95% confident that it's there. Okay, so the parameter 95% will be there on average that percentage of the time. Okay, so here again, we're going to learn about confidence intervals for the mean of the population and proportions in the population. Okay, and we will talk about proportions for the binomial distribution as well. Okay. All right, so there's a few cases that we're going to consider. The first case is the simplest, and it's probably the easiest one to articulate and to think through, so here it goes. Here you kind of know that the underlying population distribution is normal. Okay, you just know the shape of it, but you don't necessarily know like what the mean is. Okay, but you do know the standard deviation, which sounds crazy. Why would you know the standard deviation if you didn't know the mean? But you'd be surprised how often that happens. And here's an example. Sometimes like a standardized test will change. And in all likelihood, the spread of the data is not going to change. It's just going to shift around. Okay, so you'll still kind of know what the standard deviation is for the new test because you just know that the data is going to shift somewhere, but you won't know what the mean is. So it's not totally obnoxious to think that this might be a situation that you'll encounter, okay? But besides, it's just an easy case. It's one that we can talk about and absorb fully. Okay, so in this first case, we're going to assume that we know the underlying distribution is bell-shaped. We could collect data and look at histograms to convince ourselves that that's true. And we also know the standard deviation of the population. We literally know what it is, okay? And I think I wrote this on, I had this on the slides last time, but I'm just repeating this. The confidence interval is going to be the sample mean that you get. This is 95% confidence, minus 1.96 sigma over the square root of n. And I'll just say the sigma over the square root of n right here, okay, that is just that is the standard deviation for the sample mean distribution, right? It's the original standard deviation divided by the square root of n. We've already dealt with that at some point when we talked about the central limit theorem, okay? And this 1.96 thing right here, well, that is a specific z value, right? And z being the standard normal distribution, okay? And being 1.96 close to 2, isn't it? So basically what this is saying is, you know, 2 standard deviations to the left, 2 standard deviations to the right of x bar. What percentage of the data is going to be there? Well, we already talked about that rule of thumb, where if, you know, being 2 standard deviations to the right, 2 standard deviations to the left, you know, you expect about 95% of the data to be there. So that's where this 95% is coming from. But the main thing I want you to get here is this is the formula for the 95% confidence interval. Okay, you take your sample mean, you subtract 1.96 sigma over the square root of n, where n is your sample size, right? N is equal to the sample size. Okay, and you add 1.96 times sigma over the square root of n. Okay? All right. So let's talk a little bit about our interpretation of what this is saying. Okay, well, it's technically not correct to say that there's a 95% probability that mu is in the confidence interval. Okay, you could parse that out and make an argument that it is true that that's the case, but a better way to think about it is that if I were to draw a whole bunch of samples and compute the confidence interval each time, notice the confidence interval is centered at x bar. So x bar is the center, right? That's the center of the confidence interval, And x bar is random. Okay? This stuff right here, the thing I'm adding and subtracting, that's a fixed number. Okay, it's a fixed number. So what's really happening is the center of that thing is moving around. So as I get different samples, I'm going to get the same width interval, but it's just going to shift around depending on what x bar is. So the interval itself is random. The length of it isn't random, but the center is random. Okay, so the center is random, but the width is not random for this confidence interval. Okay, all that to say that if you repeatedly draw a sample and compute the confidence interval each time, so this thing, it's the same width, but it's moving around based on what x bar is, 95% of those confidence intervals are going to contain the population mean mu. Okay, so that's the essence of what we're talking about here. Okay, so if we have an infinite number of samples, if I just keep taking samples of size n and their confidence intervals, then 95% of those are going to contain mu. That's really what 95% means. I think of the intervals, 19 out of 20, 95% of those intervals are going to end up containing the population mean mu. Okay, saying that 95% probability that mu is in there makes it sound like mu is the random thing, but mu is fixed. This is not random. Mu is not random. Okay, it's fixed. Okay, so the thing that's random is the interval moving around. Okay, so that's what's sort of incorrect about saying it that way. Right? Well, in this case, we're still in case 1. So why is this true? Well, it's simple, actually. Okay, so you know that x or like that the distribution itself was normal. Okay, so even for individual data values, it was normal. So x bar is going to have the normal distribution also, with the same mean mu, but with a different standard deviation. The standard deviation is now going to be sigma over the square root of n. Okay, so x bar minus mu divided by its standard deviation, sigma over the square root of n, that is standard normal, right? This thing is standard normal. This is distributed as normal, mean, 0, standard deviation 1, okay? So what is the probability that this thing is going to sit between these numbers that we gave? Okay, well, it's just, we can compute this. That thing is like z. Okay, that just means that that's the probability that z is less than 1.96, and I need to get rid of the probability that z is less than negative 1.96. And if you look those up in a table or with Excel, you get 0.975 minus 0.025, and you get 0.95. So you get that this quantity right here, which is random, the reason it's random is because of x bar though. Everything else is fixed. X bar is the random thing. So the probability that that random thing falls in that range is 95%. And if you rearrange this thing around, this right here is saying exactly the same thing as this. Okay? You just kind of shift stuff around, multiply through by the standard deviation sigma over the square root of n, move x bar to the outside and isolate mu in the middle. That probability is exactly the same as this probability right here. And x bar minus 1.96 sigma over the square root of n, that's the left-hand endpoint of the confidence interval, right? So this right here is the left-hand endpoint of the confidence interval. And this guy right here is the right-hand endpoint. And what's the probability that mu falls in there? 95%. But the thing that's random is x bar. That's the random thing, okay? X bar is the center of that random interval. Okay, so that's really the argument for why the confidence interval is what it is, why this is the formula that really is what we want, okay? So there are other levels of confidence. I mean, you might say, why 95%? Why not be, 99%? Why not be 100%? Well, the issue is 100% isn't possible to achieve because no matter how far out I go, I'm going to always have a little bit of probability left to go, okay, in the tails. The level of confidence is the expected percentage of time that the confidence interval will contain mu, okay? So we had 95% before, but in general, you could have like 1 minus alpha in the middle, which means that, this was 95% before, right? The 1 minus alpha thing, which means I have basically alpha over 2 down here and alpha over 2 up here, okay? Just so that all total I have 100%. Okay, so in the case of 95% confidence, our alpha was equal to 0.05. Was our alpha level. The level of confidence was 1 minus alpha, right? Which in that case was 0.95. Okay, 0.95. So we can change our level of confidence. What do you think is going to tend to happen to our interval when we do that? If I raise the level of confidence, then my interval's got to get bigger. You know what I mean? The interval's got to get bigger because then that will make me more confident that my random intervals will contain the population mean. Okay? So let's see here. The 100 times 1 minus alpha percent confidence interval is given by that. Okay? Where what in the world is this z alpha over 2 that we speak of? Well, z alpha over 2 is a number, right, such that the probability that the standard normal is bigger than z alpha over 2 is just alpha over 2. Okay, so that, again, that number is the cutoff place where that happens. And then, of course, that's also going to be equal to the probability that the standard normal is less than negative z alpha over 2, just by symmetry, okay? So once I figure out those cutoffs, those z alpha over 2s, I can write down a formula for any confidence level, and it looks just like what I had before. except I had 1.96, right? So in the case of, this was 1.96 for 95% confidence interval, okay? That thing was 1.96 in that case, okay? But in general, you look for that Z alpha over 2 cutoff. It's the Z value such that above it, on the positive side, you would have alpha over 2 area above it, okay? Probability, which is also the area, okay? All right, same exact argument that we did before. Why is that the confidence interval? Well, the probability, this thing is standard normal, yes. And it's random because X bar is random, but everything else, mu, sigma, and n, those aren't random. Those are fixed. The probability that that thing falls in that range, well, that thing is distributed as Z, which is normal 0, 1. Okay. And so that's just the probability that Z is equal to or less than Z alpha over 2 minus the probability that Z is less than negative Z alpha over 2, which is, 1 minus Z being greater than Z alpha over 2. That happens twice. Okay. I just replaced that first probability with 1 minus the probability of the opposite event. And you have 1 minus alpha over 2 minus alpha over 2, which is 1 minus alpha. And again, you can rearrange things in here just using basic algebra to show that, this guy, right? So this is my confidence interval, right? This guy right here is the left-hand endpoint, and this guy right here is the right-hand endpoint. And the probability that mu falls in that interval is 1 minus alpha. That's it. There's the argument. And that's why that's the confidence interval, okay? Let's talk about one-sided confidence intervals. Okay, one-sided confidence intervals are when we are focusing on whether or not mu is just less than some specific value. We don't really care about, it being smaller than any particular thing. It's just less than something, but it could be, arbitrarily small to the left of that. Or on the other end, like, it could be greater than some specific value, okay? Well, in that case, our formula changes just slightly. We don't have to split alpha between 2 tails. We can simply put alpha in the 1 tail, okay? So in this particular case, what are we doing? Or what's up with this Z alpha over 2, or this Z alpha? Well, what's going on here is we're going like this. Okay, so Z alpha just has the property that above this thing, you have alpha percent above it, right? So that's the probability of being above this thing, okay? And this picture over here is similar, but you kind of think about, being down on the left or something, okay? So like this. Okay, this is minus Z alpha. Okay, so there's alpha down here in that case. Okay, and you just are saying, look, I want to be 1 minus alpha confident, right? So I want to be 1 minus alpha confident that I have an interval that contains the mean. So you only care about excluding 1 tail in this case. Okay. Again, the proper way to think about this is if we repeatedly draw a sample and compute the confidence interval each time, then 100 times 1 minus alpha percent of the confidence intervals will contain mu. Okay, same kind of interpretation. All right, moving on. Here's a problem. Assume that the helium porosity in percentage of coal samples taken from any particular seam is normally distributed, okay, so normally distributed with true standard deviation 0.75. So this is sigma. Okay, so that's sigma right there. Okay, compute a 95% confidence interval for the true average porosity of a certain seam if the average porosity for 20 specimens was from the seam was 4.85. So look, this guy is N, so N is 20. This guy right here is X bar, okay? 95%, 95% confidence interval, you know that's just going to be X bar plus or minus, we already talked about this, the Z value, the Z cutoff value for this guy is 1.96, and then you just take sigma over the square root of N. In that case, this is just the square root of 20. Okay, I know what sigma is. I know what X bar is. Okay, and all I have to do is just plug in the numbers and we'll get it. Does that make sense? I'm not going to go through a huge computation on that one. I fully trust your ability to actually plug those numbers in and get the confidence interval. Okay, and you just report the confidence interval as an interval. You put the left-hand endpoint and the right-hand endpoint, and you just say, here's the confidence interval. Okay. What about a 98% confidence interval? 98%. Okay. Well, if it's going to be 98%, what that means is I'm basically in this situation. Okay. So in here, I want there to be 98%, which means in the two tails, what do I want to have going on? Well, 2% split between the two tails, this would be 0.01. And of course, this would be 0.01. So that means below this value right here, and by the way, this is my Z sub, right? So let me just say this is like Z sub 0.02 divided by 2, which by the way is Z sub 0.01, right? So you have 1% above that value. Okay, so I just need to figure out, so to the left of this, that means that it's actually 0.99, right? So the probability that capital Z is less than Z sub 0.01, okay? It's 1% above, so it's going to be 99% below, okay? How am I going to figure out what Z sub 0.01 is? Okay, Z sub 0.01 equals what? Well, I could straight up use a table. You know, I could look for a number in the table that's close to, you know, 99%. Okay, or I could just use Excel. I could use the inverse in Excel. So let's actually go take a look at that. Okay, so I want a number in the normal standard distribution that has 99% of the data below it. Okay, so I'll show you one way to do this. It's to look at a standard normal table like this, and you look for a percentage that's close to 99%. Like say this one right here. Okay, what is that? That's 2.3. What is it? 2.33. Yes? 2.33 right here. This is 99%, 2.33. So it looks like Z sub 0.01, right? This is the Z value that has 1% above it, which means it has 99% below it. This thing is basically 2.33. Another way I could have gotten that, okay, just to kind of convince you of this fact, is to just use the inverse normal. Okay, so here we want Z sub 0.01. So that means that the probability that Z is greater than Z sub 0.01 is equal to 0.01. Another way to say that is the probability that Z is less than Z sub 0.01 is what? Well, 0.99. So really, what is Z sub 0.01? Z sub 0.01 is the 99th percentile. Yeah, that's what it is. So what is it? Z sub 0.01 equals what? Well, we're going to go equals normal standard distribution, or like normal standard inverse is what we want. So it's going to ask us for a probability that we want below this, and the answer here is 0.99. And boom, there it is, 2.33. We see it again, 2.33. We had it over here. It's kind of obscured, but 2.33 is what we end up getting here. Okay? So we go back over here. Z sub 0.01 is 0.033. Let's put the view to full screen now. Okay. Z sub 0.01 is 0.033. So what's the formula going to be in this case? Well, it's going to be X bar. Okay, and we have an X bar right there. It's going to be X bar plus or minus what? Look, X bar is right here. Okay. They changed it up on us a little bit, but there it is right there. This guy right here was sigma. And here's our 16. That's what n is. Okay. So it's going to be X bar plus or minus 2.33 sigma over the square root of n. And you just plug in all those numbers. You have them all. Here's X bar. The n is right there. That's really nice because the square root of 16 is just 4. And you have what sigma is. And that's going to be your 98% confidence interval. Now up here, in the 95% confidence interval, you used 1.96 instead of 2.33. And that's going to result in a smaller width interval. Multiplying by a bigger number means that we're subtracting and adding more. Okay? So that's not surprising also, although the numbers did change for this part. But if the numbers would have stayed the same, it would have resulted in a bigger width interval. How large a sample is necessary if the width of the 95% confidence interval is to be 0.40? Okay? Well, okay, so what's the width going to be? Does it matter what X bar is? Well, no. The width, okay, what's the width going to be equal to every single time? Well, it's going to be, it's going to be 2 times, okay, what is our, so think about it, it's going to be 2 times something. 2 times what? For a 95% confidence interval, we used a Z value of 1.96. So it's going to be 2 times 1.96, right? Because I just take the right-hand endpoint minus the left-hand endpoint. And then it's going to be sigma, which is 0.75 over the square root of n. And what do I want this width to be? Well, I want it to be 0.40. I want it to be equal to 0.40. Okay? So let me just write that formula up here. You get 2 times 1.96 times 0.75 over the square root of n. I want that to be equal to 0.40. And you would just solve for n. Okay, so that's a fairly easy thing to do. You just get n equals what? Well, it's going to be 2 times 1.96 times 0.75 over 0.40. All of this is going to be squared. Okay, so that's what the width is going to be in this particular case. Okay, n is going to be that, whatever that is. Okay, and actually here I'll compute that right here just for completeness sake. That's 2 times 1.96 times 0.75 divided by 0.4 is that, and then I'm going to square this thing. I get 54. Okay, so our n here ends up being 54. Okay, what's amazing is that doesn't really depend on what X bar is. Remember, The width of the interval is not random here. The center is random, and that center is X bar, okay? What sample size is necessary to estimate true average porosity to within 0.2 with 99% confidence? Okay, well, 99% confidence, that kind of changes the game a little bit, because what's going to happen with that? That means I want 99% in the middle, right? I want 99% in the middle, which means I want 0.005 in each one of the tails. Okay, so I want Z sub 0.005 in order to get this thing. Okay, and what is that? Okay, what is Z sub 0.005? Okay, let's figure that out real quick. We'll go over here into Excel to sort that out. Z sub 0.005. Okay, Z sub, let's see here. Z sub 0.005. Okay, because so what's that going to be equal to? Well, that means, think about it, if I have 0.005 in the upper tail, that means I have 99.5% to the left of this thing. So that's going to be equal to normal standard inverse, and I'm going to go 0.995. Okay, and I get 2.58. 2.58. All right, let me just write this over here. Okay, so Z, let's see, Z sub 0.005 is equal to 2.58. Okay, to the left of a Z value of 2.58, I have roughly 99.5% of the data. Okay. Okay, so back over here, full screen. Okay, so I have Z equal to that. But everything else is going to be basically the same, except I want to be within 0.2. Okay, within 0.2. So N, right? So 99% confidence. So N is going to be just like we did before, 2 times, right? Think about it. It's going to be that Z value, 2.58 times sigma, which was 0.75. And here I'm dividing by, right? I divide by the width that I want, 0.2. Remember, we had kind of solved for this before. And then we square this thing. So what does that end up being? Well, let's compute it. 2 times 2.58 times 0.75 divided by 0.2. And then I'm going to square that, and I get basically 375 or something. Okay, so N has to be 375. Okay, so that's a lot bigger. First of all, I increased the confidence level, but I also decreased the width I was willing to tolerate. Okay, I want the total width. I want this thing to be within 0.2. Okay. 0.2. All right. So let's move on. Okay. Consider a normal population distribution with a value of sigma known. What is the confidence level for the interval given by that? Okay. So that's the Z sub alpha over 2 thing in the formula. Okay, and what that means is, what's going on here? So I have 2.81, right? 2.81, and down here I have negative 2.81. And my question is, what confidence level do we have? Okay, so for instance, you know, what percentage is there right here? Now remember, this is like going to be alpha over 2, right? Which is also that, which in the middle, it's 1 minus alpha. Okay, well, let's kind of compute the probability that we're below this thing. What's that probability going to be? Okay, what's the probability that we're below 2.81? And once we have that probability, we'll be able to kind of sort this out. Okay, So let me clear this out and we'll go over into Excel. Here we go. Okay, so what is the probability? I want the probability that Z is less than 2.81. Okay, equals what? Okay, so that's equal to normal standard distribution. Okay, 2.81, cumulative, yes. I get 0.997523, basically. Okay, so 0.9975. So what this means, again, okay, so I get this, 0.9975. What this means, let me just draw the picture over here, is that if I go up to 2.81, that below 2.81, all the way below, it's basically 0.9975. But if it's 0.9975 below, that means that up here it's 0.02, 0.0025. 0.0025, which means that if I go to negative 2.881, it's the same. Right down here, it's also 0.0025. Okay, 0.0025. Which means what percentage is there in between those two things? Okay, again, these guys are like the alpha over 2's. Okay, which means what percentage is there in between? Well, I just need to take 0.0025 away out of that left tail and I get 0.995. 0.995, and that is the confidence level, is 0.995 for this particular case. Okay, so going back over here. Yeah, okay, so the answer is 0.995. Okay, that's the level of confidence, right? Or a 99, right? So this is a 99.5% confidence level with 2.81 being the thing, okay? What value of Z alpha over 2 in the formula for the confidence interval results in a confidence level of 99.7%? Okay, so once again, what are we looking for? 99.7%. Okay, so here's Z alpha over 2. Okay, what value of Z alpha over 2? Now, once again, I have to go down here also, minus Z alpha over 2. Okay, and what I'm saying here is that it's 0.997 in the middle, which means what's going on here? Well, I have to split 0.003 two ways. So this is 0.0015 above this. Okay, so this guy right here is really Z sub 0.0015. That's the percentage above this thing, which means what's the percentage below it? Right, including that tail down there. Well, it's going to be 0.9985. Okay, 0.9985 is the probability that we're below this particular thing. Okay, so what Z value do I need? Okay, so 0.9985 is what we're going for here. 0.9985 is what we're going for. So what do we do? Well, let's go over into Excel and figure that out. Okay, it's just good to do a lot of examples like this because it helps you see what's going on. We want the probability that Z is less than, so it's Z sub, what was it, 0.0015, okay, okay, this is equal to 0.9985. That's what's going on. So what is Z sub 0.0015? What's it equal to? Well, that's where I have to use the inverse thing. So equals normal standard inverse, normal standard inverse, and I'm going to give the probability below this thing, okay, which is 0.9985. Okay, so this is 2.97 is what we end up with, 2.97, okay? So going back over here, 2.97 is the answer Okay, here we are, 2.97. So this thing will be 2.97. Okay, so that's interesting. So yeah, enough about that. Okay, let me go over here real quick. I just want to make sure of something. 2.9, yes, 2.97. Yes, thank you. Okay, moving on. Okay, so here's the second case that we're going to consider together. The second case is, so in the first case, we knew that the underlying distribution was basically normal, and we knew the standard deviation of the population. Well, that's not very typical, you understand? Okay, so in this case, we're going to assume that we don't necessarily know the population is normal, but maybe we know it's like, I don't know, it's symmetrical in some sense. You could probably just get that by, or determine that by making a histogram or something. And we're going to assume we don't know the standard deviation either for the population, okay? But we want the sample size to be big enough to invoke the central limit theorem. And we've already said that can be done if n is bigger than 30. Well, it turns out that if n is big enough, the sample size, you can invoke the central limit theorem, and you could do the exact same thing that we were doing before with one slight change. Namely, instead of sigma, what do you notice there is in the, or here in the interval? It's not sigma anymore, it's S. It's S, okay? You use S instead of sigma, which is something you can get from your sample. You can go ahead and compute the sample standard deviation and get that. And of course, here's the one-sided intervals right here. Okay, so the only difference here is you use S instead of sigma, but we still use the standard normal distribution. You know, and we get the Z alpha over 2s in the same way, and we kind of think that through in the same way that we were before. Okay, this is in the case where we have sample size of at least 30, so that we can invoke the central limit theorem. Okay, so here is an example. Okay, consider a sample of ultimate tensile strength observations. Use the Minitab output below to calculate the following. Okay, we want a 99% confidence interval. Okay, so first of all, what's the mean here? Look at this. We have no idea what the underlying distribution is, but the sample size is massive. It's 153. So we can invoke the CLT. Okay, this right here that's X bar. Okay, we have a standard deviation right here. That is S. Okay. Okay, and there's like lots of other things that we talked about actually a couple lectures back. Minimum, maximum, first quartile, second, we even have the second quartile, that's the median right here. That's Q2. Okay, and we have the first and third quartiles also given in this thing. Okay, so we can invoke the central limit theorem here, and you know, it's just going to be X bar plus or minus, you know, whatever we figure out the Z alpha over 2 is, times S over the square root of the sample size. Right, we used capital N for, unfortunately, Minitab uses capital N. We usually think of that for the population, though. Okay, 99% confidence interval. Okay, 99% confidence interval. What does that mean? Well, again, we want 99% here, which means we want what percentage here? We want 0.005, half of a percent, okay? Which means that below this, we're gonna have 0.995, okay? And what did we get for that? I think it was 2.58, but we need to go check that. So I'll go do that right now just to make sure. Okay, so let's look here. Okay, so what was it? Z sub 0.005, we already computed that. Half of a percentage point is 2.58, just like we got before. Okay, so view Full screen again. Okay, so z sub alpha over 2, which is 0.005 in this case, is equal to 2.58. Okay, what's our x bar? Well, it's 135.39. What's in 153? And what is S? S is 4.59. Okay, and the confidence interval is just going to be x bar plus or minus 2.58 times S over the square root of n. Okay, that'll be a 99% confidence interval. 99% lower confidence bound. So I want to bound the population mean from below for the true average ultimate tensile strength. Well, let's see here. 99% lower confidence bound. Okay, so this, what's up with this? Well, the situation is like this here. Lower confidence bound. Okay, so 99%. All right. 99%, that means I want 0.99 above, which means down here, I want 0.01, which, by the way, if I kind of think about this up here, so this would be, this would be z sub 0.01. This guy down here would be negative z sub 0.01, right? Because up here you would have 0.01, and of course that's symmetrically the same down there on the negative end. Okay, did we compute z sub 0.01 before? If not, we can definitely do that, right? So this would be, z sub 0.01 means that there's 99% below that, okay? We could definitely do that over in Excel to sort that out, okay? Let's see. Do I have a z sub 0.01 somewhere? Yes, it's right here, okay? And it's 2.33. Z sub 0.01 is 2.33. Okay, we computed that before, so we're good to go. Okay, so we have Z sub 0.01 is 2.33. Okay, and what's the lower confidence bound going to be? Okay, well, it's going to be x bar minus 2.33 times S over the square root of n. We have all those things all the way up to infinity. Okay, so that's how you're going to get that lower confidence bound in this case. Now, I'll let you think about how to plug those numbers in, but that's how this goes. All right, moving on. So determine the confidence level for each of the following. Okay. So what's going on here? Upper bound, an upper bound thing like this. So what's this mean? That means that we're like negative infinity x bar plus this guy right here, 0.84 S over the square root of n. Okay. So this guy right here is our z sub alpha. Remember, we don't have to worry about splitting things in this particular case, but that's our z sub alpha. So what's happening is it's like this. Okay, so z sub alpha is sitting here, okay, and z sub alpha is equal to 0.84 in this particular case. And what we want to know this time is what in the world is alpha? Okay, alpha equals what? Okay, alpha equals what? Well, I think that we could sort that out. Okay, so we have a 0.84 is our number here. Okay. 0.84 is our number. I'm going to leave this. I actually am going to leave the things drawn on the screen right here, just for our, for our own sanity here. So, what is the probability that z is smaller than 0.84. Okay, the probability that z is smaller than 0.84 equals what? Well, that's going to be equal to normal standard distribution. Okay, what's the z value? 0.84. Cumulative, yes. Okay, normal standard distribution. I get 0.799. So it's basically, so what's happening with this? You basically have 80% below this thing. Okay, you basically have 80% below this particular thing. Okay, so if I have 80% below this particular thing, then what? Then that's the confidence level right there. It's 80%. That means that there's 20% above it. Okay, so 0.20. 80% below, 20% above. This is an 80% confidence level. Okay, 80% for this lower bound or for this upper bound situation. Okay, back over here. What else are they asking us for? X minus 2.05 s over the square root of n. Okay. So here we're at negative 2.05. And our question is, what's this alpha that's down here, for instance? Yes? Well, that's easy enough to figure out. Okay. That's easy enough to figure out. So let's go over to Excel. Okay, what is the probability? What's the probability that z is less than negative 2.05? Okay, well that equals what? Well, let's go ahead and just plug it into the normal standard distribution. Okay, so negative 2.05, cumulative yes, okay, and I get 0.02, okay? 0.02. So alpha is equal to 0.02, okay, which means 0.98% is above that. So that's what our confidence level is up there. Okay, so 0.98%. So let's go back over here. So this guy was 80%. This guy was 98%. Okay. And what about these other things? Okay. Well, actually, if you think about this, so like in this case, for instance, what did it look like? Well, below this thing, right? So below, this was an upper bound. So below this thing, we had 80%, right? Below this thing, we had 80%. But if I do a confidence interval, okay, if I do a confidence interval, what is going to happen? This thing is going to get chopped down a little bit, yes? So what's going to happen? Since I have 20% up here, if I kind of chop it at both ends, it's going to be 60% in the middle, and I'm going to have 20% here and 20% there. Yeah, that's what's going to happen if I have 0.84 and negative 0.84. Okay. It's 80% all the way down, but it's 60% if I just concentrate on the middle. Okay. So this right here is actually a 60% confidence interval. Okay, because I have to chop the left tail off. And what about this other thing right here? Well, okay, so basically what we did is we took, for the 80% confidence interval, there's 20%, in the tail. We put that in the other tail as well for a total of 40% in the tail, which gives us 60% confidence. We do a similar thing for this last one. 98% means there's 2% in the tail. If I put it over in the other tail, that's a total of 4%, which means I'm 96% confident. Okay, so these are the confidence levels for all these guys. Okay, those are the confidence levels for all those. Whew. Okay, that's a lot of jostling around with this thing, but it's important to be able to kind of flip through these things. Okay, I'm going to stop right there. Next time we're going to utilize the t distribution, okay? And the t distribution comes up in the very last case. Remember, the first case was, you know, we knew that the underlying distribution was basically normal, and we knew the underlying standard deviation. And then we could straight up just use the standard normal distribution, the central limit theorem. Everything worked out nice. The second case was you don't know that the underlying distribution is normal, and you don't know the population standard deviation, but you have a pretty big sample size beyond 30. Well, you can still invoke the central limit theorem and basically use the standard normal distribution table to kind of help you out. The third case is the one that's kind of still dangling out there. Namely, what happens if the underlying distribution isn't necessarily normal, like in case 2, that was the same thing in case 2, and you don't know the population standard deviation, okay, sigma, and your sample size is small. That happens sometimes when you study. Well, then you're going to have to use the t distribution. Okay, the t distribution is going to be the thing that you're using. You still are invoking the central limit theorem, okay? But you can't quite use the standard normal yet. You have to use the more conservative t distributions that are more spread out to help you out in this case. So next time we will think about that together, okay? But that's all for now. Hope you have a great weekend. You know, take care of yourselves, get some rest over the weekend, and we will reconnect on Monday.